Welcome back. The last lecture left us in the middle of the proof of correctness of the primal dual algorithm. In particular, we are interested in understanding a bound on the number of iterations. This is theorem 2 that we're trying to prove, theorem 2 from the previous lecture. What we've shown is that our algorithm, when we run it, if it terminates, it can only terminate in a perfect matching. And we know by complementary slackness that the perfect matching is going to be optimal. It will be a minimum weight perfect matching. The algorithm has three cases and several things that can happen. As we outlined in the previous lecture, it either augments the current matching, and that can only happen order cardinality of v times. And this is our anchor. We show that this has to happen at most every order v iterations. That is where we are in the proof. So our algorithm can either augment the current matching in an iteration, or shrink a blossom, or de-shrink a blossom, or it can add a new edge when it changes the dual variable. At the very end of the previous lecture, we showed that between augmenting matchings, it can at most shrink order v times, and it can most de-shrink or expand a contracted node order v times. V is a number of vertices. So there is one final other thing that can happen. In case 3 of our algorithm, which we now presented 2 lectures ago, when we're updating our dual variable, if one of the values yu doesn't hit 0 first as theta grows, that means we don't de-shrink. Instead, what could happen first is that a new edge inequality becomes tight. Therefore, changing the number of edges in EY. So we've referred to this as adding an edge. So now we have to ask, how many times can we add an edge? So how many times can we add edges in between augmenting the matching? And let's try to answer that now. So what is the picture that we have? We have our even node, odd node, even node, odd node, and then possibly other things are happening over here. And we may add an edge. Now, the edge that we add has to be some form like this, where it has one endpoint in a u that's labeled E. So note, first of all, that for edges already present, so for edges already in E dash, which recall is the contracted version of EY, these remain tight. In other words, an edge in EY remains an edge in EY because the inequality does not change. I'm adding and subtracting. Both endpoints are present. One is odd, one is even, and therefore any change in Y does not affect that particular inequality. So let's take some edge. Let's call it E. This is some edge E that is not tight with the current dual solution. I'm using EY and E dash, the contracted version, interchangeably because when we contract a subset U, we keep edges identified with the edges in EY. Okay, so let's see what this edge could be. Well, if I have one endpoint in even, then it's possible for this inequality, the sum over yu, where u is such that E has some endpoint in u. Remember, u in this case is contracted, so it corresponds to just one edge in G prime. This inequality could become tight. And why have I insisted that it has an edge, that u is an E? That's because this inequality is satisfied for every edge by definition, because y is taken to be feasible and we maintain feasibility, and I'm increasing the value of yu if u is an even and decreasing it if it's an odd. So if I'm decreasing it, there's no danger that it would all of a sudden become tight if it wasn't tight before. That's why I've assumed that u is an E. All right, and its other endpoint is some w. So where could w be? So first of all, we know that we can't have w be an odd, because if it did, we'd be in a situation like this, and in that case, the balance here wouldn't change. So in other words, then this value yu, E and delta of u, does not change. Okay, so we rule out that possibility. So what's left? Either w is in E or it's not an E. So let's first take the second case where w is not an element of even. So note that once we reset or update y in this way, what happens? We now have added our edge E to EY, but that means that once this dashed edge becomes an edge, that means that now w is going to be odd. But this can only happen so therefore this can happen at most v times, because this is the maximum number of vertices that were not in E. Max number of vertices not in E. Next, let's suppose that w is in E. Then what can we conclude? In this case, this means that w is actually in X, meaning it's exposed. And once we add this edge that's dashed, then all of a sudden we are no longer in case 3 where we don't have an X to X alternating path, but in fact we will have an X to X alternating path. And hence we have an X to X alternating path in the next iteration, which means that in the next iteration we will either find an augmenting path, in which case there will have been an augmentation, and this cycle of number of iterations between augmentation ends, or there will be a blossom that has to be contracted. And we've already bounded the number of, we've already counted the number of times that we could possibly have a blossom. So what do we conclude? Therefore, between augmentations, we know that the number of deshrinkings has to be less than whatever that initial laminar family was, but we don't care about that because we know that this is bounded by something that's order cardinality of V. And similarly, the number of shrinkings is less than our final, the size of our final laminar family. Again, we don't care what that is. We know it's at most cardinality of V. And again, what was critical in bounding this? The lemma in the previous lecture that showed that we cannot shrink and then deshrink the same set without augmenting, before an augmentation step. And again, this was just an argument about parity. And now we just showed that the number of added edges, the number of times we add edges, is less than V. Hence, putting everything together from this lecture and the previous lecture, we know we have, of course, just by counting the number of nodes, we have at most order V augmentations before we get to a perfect matching. And we have at most order V iterations of our algorithm between augmentations. And this concludes the proof of theorem 2. The algorithm, therefore, terminates in at most order V squared iterations. And finally, it's worth restating again. We've already talked about this in the previous lecture, that the algorithm can only terminate in a perfect matching. With a perfect matching in E dash, which makes X empty. And then, as we explained in the previous lecture, this means that this can be expanded to be a perfect matching in EY. And as we've now talked about many times, any perfect matching in EY satisfies complementary slackness, and therefore it is a minimal weight. It's a minimal weight matching. Two things we haven't discussed. How do we find a maximum weight perfect matching? And what about just a max weight matching in graphs that don't have perfect matching? So this is straightforward. First note that we can use the above procedure, the above primal dual algorithm, to find a max weight perfect matching by flipping the weights. And then finding a min weight perfect matching. This leaves us with the problem of how do we find now a maximum weight matching if a perfect matching does not exist. So for a max weight matching, not necessarily perfect, all we need to do is augment our graph in order to ensure that there is a perfect matching. And we're going to do this with a trick that we've seen before. We're going to make a copy of the graph. But now we're going to make a copy of the graph and between corresponding nodes just add an edge of weight 0. So in other words, if this is my graph G, I just make a copy, G prime, with exactly the same nodes and exactly the same edges. And I guarantee that this one does have a perfect matching by planting it, except that I put weight 0. So now I know how to find, I have a graph, G union G prime, with these additional edges between V and V prime. And so I know that a perfect matching exists. Moreover, it's easy to check that a max weight perfect matching in this new graph is going to give us a max weight matching in G and G prime. Because why? Straightforward, just looking at it, a maximum weight perfect matching is only going to use any of these edges, 0 weight edges, if it absolutely has to. So I will just leave this as an exercise, but it's straightforward. I'll just write verify that a max weight perfect matching in this new graph gives a max weight matching in G. So that concludes our the proof that the algorithm, our primal dual algorithm, is correct, and it also shows how we can extend this to find max weight perfect matchings and also just max weight matchings.